Hello everyone and welcome to Code Grads. Today, we're diving into a fascinating and incredibly powerful concept in the world of artificial intelligence, fine-tuning. If you've ever wondered how general AI models become super smart specialists, you're in the right place. So, what exactly is fine-tuning? Imagine you have a brilliant, highly educated person. That's a pre-trained large language model or LLM. They know a lot about many things. Fine-tuning is like sending that brilliant person to a specialized workshop. We take that generalist LLM and give it additional, focused training using a smaller, custom dataset. This transforms it from a jack of all trades into a master of one specific task or domain. Now, the slide asks a great question. If a base LLM already summarized news well, why would a news organization fine-tune it on their own articles? Think about it. They want the AI to adopt their specific journalistic style, understand the nuances of topics they frequently cover, and perhaps even learn to prioritize information the way their editors do. It's about achieving that perfect, tailored fit. Why go through this extra effort? The benefits are huge. Fine-tuning significantly boosts accuracy and relevance for your specific application. If you're in a specialized field, like medicine or law, the model can learn your specific jargon and context. Crucially, it leverages all that pre-existing knowledge from the base model. This means you're not starting from scratch, saving enormous amounts of computational resources and time. So, how does it bridge the gap when an off-the-shelf model isn't quite cutting it? It's like having a generic tool versus a custom-made one. The generic tool might work, but the custom tool does the job faster, more precisely, and with better results for your unique needs. Let's talk about the traditional approach, often called standard fine-tuning. Here, we take our pre-trained LLM and update many, or even all, of its internal parameters, its weights, using a specific, labeled dataset. Often, we'll also add or modify a final layer, like a classification head, to tailor the output to what we need, say, categorizing customer reviews or answering specific types of questions. But there's a critical consideration here, as the slide points out. Could fine-tuning on niche domains with limited data lead to harmful or biased models? Absolutely. If your small dataset has inherent biases or focuses on a problematic niche, the model will learn and potentially amplify those. Safeguards are essential. Carefully curating diverse training data, implementing bias detection tools, and always having human oversight. Now, what if we want more precise control? That's where instruction fine-tuning comes in. This is really clever. Instead of just showing the model data, we teach it how to process that data by giving it explicit commands or instructions along with examples. Think, summarize this text in 3 sentences, or translate this into formal French. This gives us incredible control over the model's behavior, its output style, and how well it sticks to specific task formats, often with fewer examples than standard fine-tuning. But what happens if our instructions are messy? If the quality and consistency of instructions vary wildly in the training data, the model gets confused. It's like giving someone conflicting directions. They won't know what to do. Clear, consistent instructions are key to success here. Training all those parameters in standard fine-tuning can be expensive. This brings us to a game changer, parameter-efficient fine-tuning, or PEFT. The core idea of PEFT is brilliant. Train only a tiny fraction of the LLM's parameters for the new task. The vast majority of the original pre-trained model remains untouched or frozen. This massively reduces computational costs. We're talking less GPU memory, less training time, and it also helps preserve the model's valuable general knowledge. Given its efficiency, are there times when PEFT might not be enough? Yes. For extremely complex or highly novel tasks that require a fundamental shift in the model's understanding, full fine-tuning might still be necessary to capture all the nuances. But for many, many applications, PEFT is a fantastic, resource-saving option. One of the most popular PEFT techniques is LoRA or low-rank adaptation. LoRa is ingenious. Instead of retraining existing large matrices of weights, it introduces small, trainable adapter matrices into specific layers of the frozen LLM, often the attention layers. Only these new, tiny matrices learn the task-specific information. We're typically talking about changing less than 1% of the total parameters. The slide asks about the rank R in LoRa. Think of R as the capacity of these adapter matrices. A very small R means fewer trainable parameters, it's faster, uses less memory, but might not capture all the complexity of a difficult task. A larger R gives the model more capacity to adapt, potentially leading to better performance on complex tasks, but at the cost of more computation and memory. It's a trade-off. How can we push efficiency even further, especially with massive models? Enter CLORA. CLORA combines the parameter efficiency of LoRa with a technique called quantization. Essentially, it loads the large, frozen base model using lower precision numbers. For example, 4-bit instead of the usual 16-bit or 32-bit. This drastically reduces the memory footprint needed to just load the base LLM, making huge models accessible even on less powerful hardware, while still allowing us to train those LoRa adapters effectively. Now, how might this 4-bit approximation affect quality? Using lower precision means there are a tiny bit of information loss. For most tasks, the impact is negligible compared to the massive memory savings. However, for tasks requiring extreme subtlety and precision, this approximation could slightly degrade performance compared to LoRa with a full precision base model. But often, it's a trade-off well worth making. What if you have several related tasks you want a model to be good at? That's where multitask fine-tuning shines. Instead of fine-tuning separate models for each task, we train the LLM on several related tasks simultaneously. This is often done by mixing data from each task during the fine-tuning process. This encourages the model to develop versatile, shared representations of knowledge, facilitates knowledge transfer between tasks, and can even improve its ability to generalize to new, unseen tasks. But could training on many diverse tasks hinder peak performance on one very specific, nuanced task? Potentially, yes. It's like trying to be a world-class expert in 10 different fields simultaneously. While the model becomes more versatile, it might not achieve the absolute pinnacle of performance on one ultra-specific task compared to a model hyper-focused only on that single task. The shared learning might lead to some compromises. Fine-tuning is powerful, but it's not without its challenges. One significant one is catastrophic forgetting. This happens when we intensely train an LLM on a new, specific task. In the process, it can sometimes lose some of the valuable general knowledge it learned during its initial pre-training. The model becomes great at the new task, but might suddenly perform poorly on tasks it could easily handle before fine-tuning because it has over-specialized. So, if catastrophic forgetting makes a model less capable overall after fine-tuning for one specific task, how does this impact its reusability? It significantly reduces it. If the model has forgotten how to do other things, you can't easily repurpose it for even slightly different tasks without further and careful retraining. This is one reason PEFT methods, which freeze most parameters, are so attractive. They help mitigate this issue. Let's zoom out and look at the bigger picture. Fine-tuning is a cornerstone of advanced AI applications across countless industries. From specialized chatbots that understand your company's products to complex data analysis tools that can decipher scientific papers, fine-tuning enables models to achieve domain mastery. And the field is constantly evolving. Smart techniques like PEFT, including LoRa and CLORA, are making these powerful capabilities more accessible by dramatically reducing resource requirements. The slide poses a key question. How does the evolution of efficient methods like PEFT make advanced AI more accessible? By lowering the barriers to entry. You don't necessarily need a supercomputer or massive datasets anymore to create a highly specialized AI. Smaller organizations, researchers, and even individuals can now experiment with and deploy sophisticated AI models, democratizing access to this transformative technology. So, as you can see, fine-tuning is a versatile and essential set of techniques for unlocking the full potential of large language models. From standard approaches to cutting-edge methods like LoRA, it allows us to tailor AI to our precise needs. Understanding these concepts is key to building the next generation of intelligent applications.